Okay, hello everyone. So my name is Sverrir. I'm the second person listed here. Unfortunately, my co-author Theo could not be here today, but I do have his slides, so I think it should be fine. I'm going to both do a slideshow and show you a live demo of our system during my presentation. So what I'm going to talk about today is, firstly, I want to motivate the need for better programming paradigms. That's going to be very brief. And then secondly, I would like to introduce a new programming by demonstration system that we have been working on in my lab at ETH Zurich. So let's talk about why is programming difficult. So I think that if you show the tools that we use as software engineers to people in other disciplines, for example, designers, that they might say something like, how can you possibly work with something like this? It's we are maybe a bit blind to it, but it's very far removed from the actual tools and systems that we're trying to design, the way we do our work. In other words, I think some people might find this just totally incomprehensible. And maybe a better question than why is programming difficult would be, in that case, why do they make programming so difficult? Like, isn't there a different way that we could do this? Couldn't this there be a bit closer connection to how we design software and the software, the final result? So our goal with our system is relatively modest. It is that if we make this assumption, which is pretty grand, that we do have an algorithm in mind, that maybe we could come up with some way to make instructing it to the computer a little bit more intuitive. So if we try to motivate this a little bit just by talking about the perspective of things, let's do a small puzzle. So maybe some of you have seen this before. We have here a set of cards that have the property that on one side they have a number and on the other side they have a letter. And there is a simple rule that we should follow. So if a card has a vowel on one side, it has a rule that it's an even number on the other side. So which of the cards do you have to turn over to check if this rule is correct? So you would have to flip over the first card, right? What about the second card? Can someone tell me which cards we should flip over? The first and the last. Any else?
Just the first one.
Just the first one. I think we need to flip over the first and the last one. But if we just reframe this a little bit into something that we can understand more easily, isn't this problem a little bit more easy to understand? Just asking, we will see it immediately, but we would need to flip over the card with the beer and the card with the 15. And this is just a matter of presentation. So our goal, coming back to it, is that if you have an algorithm that it should be a little bit easier to instruct it to the computer, that it should be relatable to the user. So moving forward, I think that if we talk about the model of the world, the purpose of code should be, like in the words of Brett Victor, to manipulate data. But unfortunately, we never see the data. Typically, we don't, for most programming languages. And it is a little bit as if you are a painter, but you're blindfolded. You don't see what you're working with. So this is the programmer, and this is the state. we think that the program state should be relatable, visible, and editable. Relatable, like we saw in an example about underage drinking, and also visible and easily editable, ideally with direct manipulation. So the way we do this for our system is that we choose to represent the entire state of the program as a graph. First off, because we think that graphs are easy to explain. They have great modeling power, and they are relatable because people are, whether they realize or not, they're pretty used to thinking about real-life things in terms of graphs. So I think at this point, I would like to show you a demo of how the state in our system, Alcott, works. So let me see if I can make the switch. This is our website. You can access it if you would like to on alcott.org. Let me create a new workspace. Here on the right side of the screen, you see our state. Right now, we just have a single node. But if we would like to add another one, we just select from the operation view right on the bottom, new node. We can select a node and perform some operation on it, such as increment or add child. If the connected component is a tree, it is rendered like this. If it is an inverse tree, we can connect it like this, connect it like this. But we have some layouting going on so that we can also show graphs in general. And then we can do all kinds of operations. We can remove edges, for example, and we can store custom values. And this is all very nice, but I haven't actually shown you any programming yet. So if we move on to how we can use this environment with this editable and relatable graph, maybe we can draw a comparison with robotics. So a robot would typically do things first by sensing input. It gets some input from its sensors about its environment, and then it can ask some questions. For example, where am I, or where am I going, what is my speed, and so on. And then lastly, it can perform some actions. For example, if it is a vacuum cleaner, to do some vacuuming. We would like to kind of use this model of robotics for our system. So we would like to structure our operations in 3 simple stages: input, query, action. So input states, first off, what nodes do the operations see? Secondly, we would like to be able to do some pattern matching on them. In the query states, we can ask questions about nodes and their values. And in the action states, we can manipulate the graph, the state graph, based on the results of our queries. And this is kind of what you do in a traditional programming language like Java, but it's not as transparent. I think if you do a comparison between, when you're assembling furniture, if you would like to follow a set of instructions like this, or if you would prefer to see a diagram, I think for most people, especially those that are not that are new to programming, that being able to see the state would be immensely helpful during the programming activities. It's pretty sad that typically when you're doing your work that you don't, the programming language doesn't have much to do with what you're actually working on. So our insight is that programming should resemble what happens when the program runs. So we have this ideal that we can do programming by demonstration, that we can use the same environment as the playground, and that the user can show what they want the system to do. So let's move on back to an environment and show you how we have implemented this version of our 3 states operation definition. So in our operation panel, we can define a new operation. So let's say that we just want to do something simple, such as incrementing a child. So here, in the beginning, we have an input state where we specify how many nodes the operation should act upon. In this case, maybe we just want 1. We can skip the query states for a simple operation like this one and just go directly to our action states. And say, over here, we would like to increment this node and append a child. And then when we exit the demonstration view and perform this operation on the single node in our graph, all it'll do is to add 1 to its value and append a child. Moving on to the query states. Let's say that we want to define an operation that can find the max value from 2 nodes and store its value in a 3rd node. So we have 3 nodes, A, B, and C, and let's call the last one out. In the query states, we can ask, is the value of A, is it lower than the value of B? That is this query here on the right bottom. I can just click on it and move on into the action states, and I can say, if the value of A is less than the value of B, then if it is not, then I just move the value of A into out, copy value. If it is less, then I move the value of B to out. And let's try this. Let's give it some values. And then we can just select the nodes that we were working with, click on Get Max, and it will copy the value of the larger node into the output node on the right. And then lastly, I can show you how we can implement pattern matching on the input too. So we may have an input node that we expect to have some children. In that case, I go into the pattern matching view on the bottom of the input states, select append child. Maybe I will select 2. I will call this increment right child. And in the action states, I will just simply increment the value of the child to the right. And that's all there is to it. Let's create a tree like this, select increment right child, and you'll see that the right child increments by 1. So these are very simple operations that we can do with the system. Moving on. You may have noticed that so far we have not shown any looping or iteration in the system. It's missing. Explicit loops would complicate the interface a lot because we would really like to it would introduce nesting, which we would really like to avoid. One issue with an interface like this is that cluttering can happen very easily. So if we could just reuse some nesting that we already have via the operations applications, perhaps we can do it in a very simple way. Maybe some of you thought when I was showing the system that we can just use cell reference. We can call the same operation and nodes that we are already defining. So we would use recursion. So let me just show you as a last example how we could implement Fibonacci numbers. So here's a workspace. Let's delete the state. I'll call it Fibonacci, and maybe select some nice icon. Let me see. We have a lot of different nice icons here. For Fibonacci, we would like to implement it so that we have a linked list of the first n Fibonacci numbers, and the operation should take as an input some integer that should specify how many new Fibonacci numbers we should append to this existing list. So first off, we add one input which represents our list. We use pattern matching to append a parent to this input. And then we have another input which we will just call the index. In the query states, we check is the value of index is it 0? And in the action states, we do this check. We will check is the value of index equal to 0. If it is not, what we'll do is that we'll append a new value to our list at child. We will take the sum of its parent and grandparent value and replace its existing value with the sum. Then we will decrement the value of index and we use self-reference the Fibonacci function we just defined on the new child and index. So let's define the first two Fibonacci numbers. And let's say that we want to generate 7 new ones. So I'll give this value 7. Select the last node in the list of Fibonacci numbers and click Fibonacci. And you will see we get 7 new Fibonacci numbers very seamlessly. We can also do binary tree insertion. I have a little bit of time left, so I can show you how this works. So here's a video that I'm going to share just because I was worried about if I would have time for this or not. So here we do very much the same thing. We have a root node, and we have a node that we would like to insert into a binary node. We call the node that we would like to insert into the tree, the binary tree, new. We do a query, and we check, does root have any outgoing edges, outgoing nodes? And if it is not, then we simply take new and copy its value. And then we add 2 new leaf nodes with the values 0. Then we define a second operation called insert into non-leaf, which works similarly. We define the root node and the node that we would like to append into the tree. We append children. And in the query states, we check if new is less than a value of root. If that is true, we take A and insert new as a child node into A. If it is not, we do it on the right side because it's a binary tree. And then if root does not have any outgoing edges, we call the operation we just defined recursively. And now you can see how this works. We can insert 10 into an empty tree. we can give it the value 4 and insert it again into the tree. And it goes on the left side because it's a binary tree. We give it the value 7 and do the same thing. It goes on the right. It follows a very beautiful pattern. Let's do one last example. 10, 11, and you see this would go on the right side, left of 13. So you see. Just using very simple input query action view that we just talked about. So go back to my slides. The key ideas is that the program state is should be relatable, visible, and editable, as opposed to not really visible and hard to grasp, as the Java code I just showed before. Instead of keywords having no inherent meaning, we ask that programming should resemble what happens when the program runs. And lastly, we replace programming structures with nesting that makes programming very complex, with structuring operations in 3 simple stages with recursion. And if you would like to try, you're very welcome to visit alcott.org and go through our tutorial. That should explain some of the details a little bit better. So, thank you.
Thank you, Eric. Let's take some questions from the audience. Please indicate questions. Microphone. Okay. Good. Thank you. There's a question over there. Yes, thank you.
Me again, I'm so sorry. I've got the impression that one of your main goals is to illustrate and clarify semantics by playing around with real examples. Is that true?
By playing with weird examples.
With real examples.
Real examples, yes.
Yes. In this case, is it true? This impression. For real computations, you won't use this system.
It depends on what you mean by real. I mean, we're not doing software engineering yet, but
yes.
it's.
What do you mean? But we are using real figures and doing calculations and so on.
Right. Yes.
And showing the results.
Right.
I think that would be very useful. Your first example was very helpful in this respect, because natural language is a hurdle. And even here, I got the impression that the if was partially misunderstood as if and only if, which would be equivalence rather than implication.
Right.
And so it's very good if you have examples which make exactly clear what you mean, so that misunderstandings are prohibited.
It's a great point. Thank you.
Yes, I'll let her know. Sure. I shall carry on while you're busy. Yes, more questions, please. Hello, thank you very much.
Hey, thanks. It looked really interesting. I was curious. So you already, like, sort of for the number, like when you show of this library of operations that you can do based on, for example, what the user is selected,
right?
That already looked sort of, okay, so far you trimmed that down to like, I think sort of 5, 6 or so at a time at most. But if I think about this in, let's say we stay with graphs, but we maybe have, instead of just integers, we have like strings or something else that's going on. It seems like this is quickly going to explode in a sense, like in how many operations there are possible and like making them selectable. Do you have any thoughts on like how to handle that basically in a...
Yes, we do. So our idea is that we would introduce templates that represent a more complex structure. Okay. So that if you, for example, have a string, like you said, that it could just be represented as a list of nodes. And if you want to see a detailed view, you can select on the template and see how the graph structure looks like. But generally, you wouldn't need that. So it's just represented as a string on the screen. And you could do that for all kinds of other structures or types that you would like to use when programming. Does that make sense to you?
Sounds interesting. Maybe I'll play around with the tool with it. I don't know if that's like sort of hypothetical that is that already in the current tool?
We mentioned it in future work, yes.
Oh, so it's more like future work. Okay, so it's not built ready yet.
No.
Okay,
I see. But I think it's I don't think we need a lot of additional research insight to implement it. It's just a matter of implementation work.
Okay. Thank you.
Thank you. We're going to take one final question. Thank you very much.
Thank you. Yeah, it's a really interesting idea. I also have a question about what happens when the code becomes more realistic or
Right.
complex. So, for example, in the conditional, you had if this is less than that, then, but you would never program like that. You would usually have what happens if the other one's larger or if they're both the same.
Right.
How much does that complicate your diagram approach?
I think we can have the option of introducing additional queries that the user can use. So to simplify things, it's a very modular system that you can use to you can use existing operations to build new operations, and we have library support that makes programming a lot more straightforward than if you have to
Okay.
implement everything from scratch. We
Okay.
do notice that things get cluttered fast for more complex operations. For example, if you want to implement a sorting algorithm like merge sort or quick sort, that you have all kinds of lists and the nodes lying around. But we think we can solve this by abstracting one level higher, where you can group similar elements together, and you can hide a detailed view of a connected component into a single node.
Okay. All right. Thank you.
Thank you very much. Ooh, go on. One very last question. Make it quick.
sorry.
Thank you. No, that's fine. Please.
You currently have, let's say, 3 tabs for your input, your query, and your action. Did you consider to put that on one screen? Because now you have to kind of remember between the two things.
So if we can have this demonstration, this playground view that we saw in the beginning, and this operation view in the same
That you
view.
put, yeah.
Right, yeah, I think it would be a great idea. That requires some additional insight, I think, into making it natural, but it would be great not to separate them.
Thank you.
It's a great question.
Thanks. Let's thanks Ferrier one more time. Thank you.